Here we go. So I want you to remember, when it comes down to functions, I don't know, you don't have to really write this down, but once you have your equation, folks, it's usually what's x when y is given, or if x is given, what's y? Like, that is the theme, right? So once you know your equation, you can answer that. So they will find clever ways of turning that into a word problem, but really this is what you're after. So you're either using y2 is equal to something, second trace 5, or using second trace value, right? Enter that x value and then find out what y is. That's what it's all about, right? So that's the big theme here. So don't let the functions scare you. You just type it in if there is an equation. If there isn't one, you come up with points to help you find them. Okay, so let's talk about a few aspects before I'll show you the iPad graph. On the iPad, I should say, exponential logarithmic functions are called inverse. Okay, inverse functions. Here is the big thing you need to highlight. It's because the x and the y variables switch. I will say this. Maybe up here because I need a bit room. Time is often the y variable, and that's what can make this a little confusing. But I will explain that a little later. But for now, let's just highlight that time is often the y variable. So don't be alarmed when you're doing logarithmics, and you have time as on your y-axis. It throws a lot of students off. Don't worry about it. It's all right. Okay. The expression log is known as the common logarithm, and it's expressed as a base 10. The expression lnx is known as the natural log, and it is expressed as a base of e. This is Euler's number, remember? So that's my base. You don't need to freak out over this too much. Just follow along for now. The graph never crosses the y-axis. This is very important. Which one did the exponential never cross? The x-axis, remember? Logarithmic never crosses. I will go for arrow and just say, hey, you should make note of that right away, that it will never cross the y-axis. Both log and natural log have the same properties, but when graphed are slightly different. A logarithmic equation has the general form of, they are both the same. And on your calculator, if I could ask you to look at your calculator for a moment. There's a log button, there's a natural log button. So you just have to make sure that if we give you the equation that you press the right button, okay? However, most of the time it's natural log. That's all you need to remember, okay? Just type in the right button and you'll be fine. So y is equal to a plus b times log of x, or the exact same thing, a and b is still here. One is log, one is natural log. This is important here. What does a do? A, this one right here, or there, gives the point 1a, okay, on the graph. Always include that one. Okay. Make sure that point shows up on your graph. 1a, it's not 0a. Understand that it's 1A. I would have, like, later as you build your study sheet, make sure that is on there. What does B do? B, which is this one here, so regardless of which version you're provided with, B is right in front of log or natural log. It determines, right? Determines if it's increasing or decreasing. Watch out, right? If B is bigger than 0, not 1. If B is bigger than 0, you have an increasing function. If B is less than 0, you have a decreasing function. I would say this though, if you're ever in doubt, just type it into your calculator, look at the graph, you know for sure. I just sometimes think it's gonna take you too much time. It's gonna take time away, but I like for you to know that when you graph something, you can look at the equation and be like, oh yeah, that makes sense. That's what I want you to be able to do. So that you're not like, wait a minute, why is it going down? I have a positive, like B is bigger than 0. What's going on? That means you typed it in wrong, perhaps, right? So maybe I should say this. B bigger than 0 means positive, right? B less than 0 is negative. So same thing. If B is negative, so if you have a negative here, it'll be decreasing. If it's a positive, it'll be increasing. Couple of things here. Let's add our arrowheads right there. And I know this graph is a little misleading because it looks like it's touching the y-axis, but I promise you it's not. It's a screenshot of what I'm about to show you. Okay? So this is the natural log here. Let me just show you that, and I'll take it away in a bit. So here, watch this, the point, this is a logarithmic, right? I'm going to label 1A. So this point right here, what is A at this moment? A is equal to 3. See that? If I were to highlight that, it's 1, 3. So if you were to slide this, right, according to, so whatever I make A to be, right, that's what is going to be on your graph. So essentially the value of A could also increase or decrease this whole thing, shift it vertically up and down. But the most important thing is that that number, whatever A is, in this case it's 2, it will be 1, 2, right? If I make it 3, right, then it's 1, 3 on your graph, see? That's one important feature. The other one, let's get rid of this one. I'm going to do a natural log. I did a log, and this is natural log. It's the same thing. If I did them side by side, let's do them side by side. One is just slightly, looks slightly different, but they behave the same way. Okay, so you don't have to worry about that. When you graph it, you'll go about it the exact same way. But 1A, right? So 1A, this A is the same as 3, is still on there. Okay, so if whatever I make A, whatever I change it to, like say it's -5, let's say, then guess what? It's going to be 1, -5, okay, on the graph. Most of the time, it's going to be in the positives. Another thing, look at B here. Watch what my pencil does. It's positive. So as long as it's positive, it's going to be increasing from left to right. But as soon as I turn that into a negative, let's see here. If I turn it into a negative, it's -2 now. B, the value of B, this one here, is -2. So it's decreasing from left to right. Okay. Isn't that cool? I don't know about that. I don't know what you determine as cool. But another thing is it looks like it's touching the y-axis, but right, if I zoom in, just keep zooming in, it'll just never touch it. Even if it looks like it will, There again, it looks like it will. If I were to zoom in, it just keeps on getting closer and closer and closer, but it never actually touches it. So if you're trying to, if you plug in a y-intercept into your points and you're trying to do a regression with logs, it's going to give you an error. It just can't be, right? So keep that in mind. Okay. All right. That's logarithmic, folks. Because look, we did exponentials not too long ago, right? This is what an exponential looks like. Okay, it's either like this or like this. A logarithmic kind of flips it on its side, so the graph is always going to be on this side of the y-axis. Okay, so let's keep going. There's something called, yeah. In terms of the shape, one will be a little, as I was showing you, one is like a little tall. Like if you were to do them side by side, everything else the same, one would be a little, it will be flatter than the other one. Okay, good question. So if the question literally says log, you press the log button. Okay. If it says ln, you press the ln button. If you do a regression, you're probably wondering, what about a regression? It's always going to default to this. It's always going to be natural log if you're doing a regression. So maybe come with me and look at the options here. So go stat, calculate. See that one right there? That's natural log regression. There is no such thing as LOG, logistics. That's not what we're looking for, right? But there's no such thing as LOG regression. There's only natural log. And this is very important that you don't mix them up. This is a linear regression. That's why it's A plus BX. This is the natural log. This is the one you would be using if you did a regression. But that's not today. We're not going to do regressions today. We're going to do that tomorrow. Okay. All right. Couple more things. Increasing. So the end behavior goes from Q4 to Q1. Okay, that's an increasing function. Guess what? Where is this one coming from? Q1 to, where is it going? It ends up in Q4. So they both have the same end behavior. Okay. I'm going to add that here. And there's also the asymptote that I'm gonna use green for it. So I would use a color. So this, the y-axis in this case, it never crosses it. Okay. This is the x is equal to 0 line. And we call that the asymptote. If you've got the x is equal to 0 is the vertical asymptote, it means it just never touches it. Okay. That's, for both increasing and decreasing, the following is true. Okay, so for increasing and decreasing, the end behavior is always Q1 to Q4. X-intercepts, there's always one X-intercept. But when it comes to Y-intercept, use a different color here, there are no, oh wait, what's that typo? You see that? There are no Y-intercept. Can you change that? There are no Y-intercepts. right now, as it stands, my domain is 0, not including, all the way to, like, it keeps going out to infinity. And my range goes from negative infinity, because this thing still keeps going down indefinitely, all the way to positive infinity, round brackets. Or if you want to do set notation, this would be y is greater than 0. Sorry, not y, x. X is greater than 0. Or this would be y is belongs to all the real numbers. So all numbers, all real numbers would apply for the range in this case if there's no word problem attached. So I'm going to go straight to a word problem. Let's go to 38. Is right here. Okay. The equation that models the time required to reach a particular radiation level after a radioactive leak is given by the equation blah blah blah. Right? That's what I call it. Watch carefully here. Where T is the time in years, and I is the target radiation intensity to be reached. The initial radiation intensity after the leak is estimated to be 1600 millisieverts per year. I've never used this, but the reason I included it is because whatever scary units they attach, this is what we measure radiation in. Okay. Radiation level. Okay. It's measured in those units. Now, when you look at this equation, it's very important to tell yourself, what does x represent? What is y representing? Where does the x variable normally go? When I give you an equation, where does it go? Is it this one, or is it whatever's on the right side? Right? So whatever's on the right side is your x variable. So this is technically our x variable. So what is that? That would be the intensity. And what would go on the y variable? It's this one, isn't it? That is always my y. The one that's on its own there is the y. So what is that? That would be time, correct? But Mr. Jackson, how is time the y variable? Since like grade 9, we've always been told that time is our x variable, correct? And that's where you have to be careful. This is the one exception for logarithmic. You have time in the y. That is okay when you do logs. Okay. I don't know. It's like, I think it's worth mentioning, right? And how do you know for sure? Look at your equation. Just look at your equation. This is x always. Whatever's on the right side is your x. That goes there. This is your y. It goes there. Okay. Let's graph this. Enter it into your calculator. So we're going to go to y equals. Clear whatever is there. Turn off plot 1. So let's go 266. Oops. 266.44 minus 36.36. Which button are we going to use? LN, correct? Press the LN button. It's right here. underneath log, and then just x. You just put the variable x in there. Before we hit graph, what do we know? I'm going to do this on the side here. There's a point 1, 266.44 on this graph, correct? This is 1A. Right? I know that already because this is A right here. This is B right there. B is negative, correct? It's less than 0 or negative. So what is my graph? What do I expect my graph to be? If it's negative, it's decreasing from left to right. So I expect something like this. Correct? But I want the point 1 to 66, right? 1 to 66.44 is going to be on there, right? 1, and then you go up to 166 along the y. So we know a lot of things already. I should have said decreasing, right? Decreasing. All right, so let's graph it. Let's see what happens. I'm just going to give it a try. Not a very good graph. So let's change our window here. X min, make it -1 or something. X max 100, sure, let's keep it like that. This is where probably you shouldn't have 10,000 for your Y max because right now we know that 1 to 66 is on it. So what should we go? We should probably go with 500, 400, something like that. I'm going to go 500 and hit graph. There it is. So it's kind of weird. It almost makes it look like there's nothing here, but there is. It's just you would have to zoom in more. But now I see my graph. I start to see it. So let's leave it like that for now and change it if we need to. You want to see my window one more time? Look at it. I'm slightly in the negatives everywhere else. In the mins, the max. Don't ask me why I came up with 100. I just tried it. You might have to change that later. Zoom fit. I don't know if you want to try that. You can try it. See what happens. And remember, Lord of the Rings, you shall not pass, right? Like this is, it will not pass the y-axis, right? It just won't. It's a logarithmic. Make a graph of the time required as a function of radiation target. Okay, let's make the graph. Not too big. So I want you to try these after we're done today. I know the time is running out. It's going to be short, but what goes here, guys? What's on the x-axis? It's not time. What did I determine way up here? Intensity. And this is MSV per year. Okay, that's just the unit that this question is using, and so that's what I'm going with. They will always give you the unit. Yeah, because no, just go with whatever units are attached to intensity. I know it's weird. It's almost like if you were to measure, I have to come up with a good example there, but just stick with it. Because we know what is our, this will be time. Oh, okay, we're told that it's time in years, so we're going to put years here. But leave this as is. If the question says like this is how you measure the other one, just use everything that's there. Okay? That's the safest. That's all I can tell you there. So this would be time in years. Now, I don't want you to see this and start doing this with exponentials, with cubic. oh, time is on the y-axis, it's okay, right? Just for logs, okay? You get to do that. What is my scale? Well, 1, 266.44 should be on there. So I'm going to go 100, 200, 300. Let's go 400 just for good measure. So this is like that. What about here for my x-axis? Does it ever cross the x-axis? And the answer is yes. They do have, logarithmics have x-intercepts. You should probably include that. X-intercept, y2 is equal to 0, second trace 5. Let's go find that. And I have a feeling we're going to have to change our window here. See that? They're not even close to meeting here. So I'm going to increase my x max. I'm going to go 500. Go big or go home. Still not. Okay. I'm going to go 2000. Enough of that. There you go. Boom. So that's 1522.08. 0. Okay. So that is my x-intercept. That's what I'm going to use to guide me here. We're not told anything else, so that's what's going to happen. So we're going to go 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600. That works pretty good. So 400, 800, 1,200, 1,600. This is 1,400, 1,500 is just past closer to 1,600 here. I have 266 over here. Don't pack yet. Okay, let's finish this. You would probably want to find one more point somewhere along the line here. I will give you, I did 250. So I went 250 is right about there. 1 second, guys, 1 second. I don't do this very often, but I want to finish this. So you got to make sure you go like this, and then over here, and then keep going. This actually keeps going up like that. Okay. Can I ask you, I really want you to try the pages that follow, okay? Do a couple. So let's go 38 to, or page 39 to 41, okay? You should be able to do it because I give you the equation. You just have to enter it and answer accordingly. And remember the theme. Remember the theme is I give you the x, you find the y. I give you the y, you find the x, okay? We'll do more of this tomorrow, all right?